Well, this chapter focuses on, this is chapter 3 from the Redwood's pre-algebra book. It starts out talking about the fundamentals of algebra, and it gives you a history dimension to algebra. I believe that math history is very important in understanding where some of the topics came from and how understanding the history, I believe understanding the history can inspire you to go far in math. It talks a little bit about algebra having its roots in Baghdad, Iraq, and then also it talks about the Babylonians solving quadratic equations 2000 BC. So you notice that as the Babylonians, the Hindus on the Indian continent were also working on algebra. Along with the invention of the symbol for zero, and then the book talks a little bit about René Descartes, the Frenchman, as well as the role that the Gutenberg press played in learning and life. So I think that it's always good to spend time reading some of the history. You can see that history on page 171 of the book, talking about the fundamentals of algebra. In talking about math expressions, 3.1 of the book focuses on explaining how you take words, for example, and try to put them into a format that involves numbers. And that's a very important skill in mathematics, knowing how to take words and put them to numbers. So the first section talks about that. When we use letters in mathematics, one of the important things to keep in mind is that the letters are just showing the generality. So if somebody says John has twice as many toys as Peter, and somebody was to represent it as 2x, we don't know what x is, but x, whatever x is, John would have 2 times x of that number of toys. So for example, let's say Peter had 20 toys, and we said John has twice as many. That means that John has 40 toys. So x in this case is 20. So 2 times 20 is 40. So whenever we use the word x, we're basically saying we don't know what this is, or just something to represent an unknown, and that unknown depends on what, again, the number might be. In this case, it was 20. So the chapter in 3.1 talks about what a variable is, and it's a symbol that stands for a value that may vary. That's what the word variable means. And then when you talk about expressions, there's a very good table that is given on page 173 when you're looking at the phrase and what it translates to. So for example, if it says what is the sum of x and 14, that's the same thing as saying x plus 14. So when you say the sum of something and something, you're adding two things together. When you say the difference, then you're subtracting. What is the difference between y and 12? That's saying y minus 12 basically. So that's the difference between them. Or when we use the words like 10 is less than something, that means that thing, so let's say 10 is less than b, for example. That means that b minus 10 is what this expression will be. An expression usually, again, is, so you have expressions and equations. An expression is sort of laying the groundwork for what could go into an equation. With an expression, you're not looking at the equal sign yet, except if I tell you, so 10 is less than b and equal to something, for example. Now, when we say something is equal to something else, we're bringing in equations. So if someone says 13 more than x, for example, it means x plus 13. So just very good to spend some time looking at the examples, reading through the section for this one, and it'll be very helpful. In the practice problems, the emphasis is actually more on substituting values in, and that's important to keep in mind. So we start out by talking about translating words into math expressions, and then we transition into plugging in values for variables. So I want to encourage you to do the section where it says you try it for each of these ones. So the one on page 172 talks about 13 more than x, which would just be 13 plus x, or x plus 13. Why are we able to say 13 plus x or x plus 13? Because of the commutative property of addition. We can do that. If we say 12 fewer than y, that would be y minus 12. 12 fewer than y. And that's given on page 172, 173. So it talks about the phrases. It gives you some examples. Go ahead and read that and try some of the practice problems there. For this section, I highly recommend just focusing on reading and looking at the example and then doing the problems that say you try it. So that's what we have for this section of 3.1. It's focused on plugging in those values when you're looking at the application. Let's look at, so that was actually 3.2, I apologize, where it talks about evaluating the algebraic expressions. I opened to 3.2 practice problems ahead here. But in 3.1, they do give us some problems. So let's look at some of those problems. Let's look at like number 1 says 8 times the width n. So this is the section where it focuses on, like the odd problems you have in your solutions manual. And so when they say 8 times, they said 8 times the width n. So if something is 8 times something, it's 8 times n, like that, right? So we had that one as 8 times n when we say 8 times the width n. 2 times the length z. So number 2 says 2 times the length z. 2 times the length z. That would literally be like saying 2 times z. So we see another example there where we're just applying the conversion from the word problem to a way that shows the number and the letter together. The next problem, number 3, says 6 times the sum of the number n and 3. So when it says 6 times, right? So for number 3, it says 6 times. Okay, so we know there's going to be a multiplication. That's what the dot represents here. So this is representing multiplication. So we say 6 times the sum of the number n and 3. So the sum of the number n and 3. So n and 3 are adding together, and then we're multiplying it by 6. So you write it again. It's almost like you're learning the grammar of mathematics, if you want to put it that way. And so that is what we do for that one. 6 times the sum of the number n and 3. The other problems, again, give us a lot of practice on how to apply this principle. Let us look at what the goal is. So let's see. We've already done number 1. We've done number 3. We're focused on odd problems throughout this chapter. And so if you're doing the odd problems, just go ahead and give it a try all the way, the odd problems all the way to number 19. So you're starting from number 1, you're going all the way to number 19. Problems like number 21, 23, and 25, I could quickly discuss. It says representing numbers. Suppose n represents a whole number. What does n plus 1 represent? Well, that's like the whole number plus 1. That's what that would represent. Since n, if you're looking at a whole number, you can think of a number like 0, 1, 2, 3, 4, 5. Any of those numbers can represent n, and that would just be using like 3 plus 1 or 4 plus 1. That would be an example using those numbers. So that's what number 21 is talking about, and this is preparing you for 3.2. In number 23, it says, suppose 2n plus 1 represents an odd whole number. How would we represent the next odd number after 2n plus 1? Well, if it's an odd number already, the thing about odd numbers is we have 1, 3, 5, 7, and so on. So if you have 2n plus 1 and it's odd, you would have to add 2. So 2n plus 1, and then you would have to add 2. Why would you have to add 2? Because if this is an odd number, the next odd number will be if you add 2, because odd numbers change by adding 2 from one to the next, right? So you start at 1 and you can add 2 and so on and so forth. Number 25 says Steve sells twice as many products as Mike. Choose a variable and write an expression for each man's sales. So one sold twice as much as the other, right? So if Mike sold, W products, if Mike sold W, so let's say he sold W products, and the fellow Steve sold twice as many, that would be 2 times W. So that's what you would get for the conversion from words to taking it from words and then trying to get it into the form of an expression. For problems like number 5 and so on, since we're doing number 1 to 19 odd, number 5 says the demand B quadrupled. That means you're taking B and you're multiplying it by 4, right? That's what quadrupled means. Number 7, the speed Y decreased by 33. So think of a real world situation where the speed limit was 45 and then it dropped to 30, right? You would say the speed limit dropped by 15 or decreased by 15. So that would be like Y minus 33, right? That's for number 7. So I'm giving you some extra notes, even though you're doing the odd problems. I'm giving you some more examples using the odd problem. Number 9, 10 times the width n. similar to number 1 in dealing with something times, so this time is 10 times n. And then number 11, 9 times the sum of z and 2. Very similar to number 3, where you add z plus 2 and then you multiply that by 9. Very good. So yeah, try these problems out. Let me know if you have any concerns with this section. It's a very important section to lay the groundwork for just knowing how to convert words into expressions and then simplifying those expressions. You have a wonderful day, and thanks and keep up the good work. Let me know if you have any questions again. Thank you very much.